requires this. And then there's another thread here, let's say thread 0, this is thread 1, this is resource 0, this is resource 1, right? So it requires R0, then R0 is owned by T0 because you acquire the mutex, and the mutex actually allows T0 to use this R0, so it's protected by the mutex. Okay, the same thing when you request here to acquire R1, R1 eventually will be given to T1. Okay, what happens if, let's say, now thread 0 also want to acquire it? So there are two mutex here. There's mutex, this is protected by mutex 1, this is protected by mutex 2. This is a bigger one. So you got two different mutexes. So this one is protected by mutex 1. This one is protected by mutex 1. Okay, mutex 1 and mutex 0. So I acquire the mutex. If I succeed in acquiring this mutex, that means R0 is owned by T0. Remember, mutex is mutual exclusion, meaning that if I manage to acquire it, I manage to use it myself. Okay, so nobody's sharing. The same thing on here, T1. If you manage to acquire mutex 1 successfully, acquire mutex 1, then you can use this resource 1. Okay, it can be printer, it can be a file, it can be any data in the memory, okay, which is protected by the mutex. If once you acquire successfully, you're able to use this, and you're using the T1 successfully acquire mutex 1. So you can use this R1 without any risk or any problem. Okay? But what happens after it acquires mutex 1, he owns it. T0 acquires mutex 0 and he owns this R0. And it's not satisfied because he has to process the data maybe and then put the data in this resource. Let's say this is a hard disk, break of hard disk. Now you want to print. But this printer is already owned by another thread. So you try to request it. And it will block. Why it blocked? Because T1 is right now holding this resource. It acquires successfully the next one. So T0 is going to block. So this block right here. Same thing here, T1 wants to maybe also acquire this R0. So you will try to acquire and this itself can block. So you can see that here it blocked, this one blocked as well. Now they are in deadlock situation, right? Because now it's impossible for them to progress, and it's impossible for T0 and T1 to release their respective resources, right? Because this guy blocked already, you cannot execute any other code. This guy also blocked, you cannot execute any other code. That means you cannot release either this or this, so deadlock. This is the serious problem. We don't want to get into this deadlock. Once you get into deadlock, your system hangs. Here we have two options. The first option is the operating system kill one of them. Kill one of them and then release. To release whatever resources that is owned by them. But this has problem. Let's say I write a file, I write halfway. Okay, and then I kill. What happened? The file is not written to me. Data is not written. Okay, so killing is not a good option unless you have a way to restore the data. That means you kill this, you can restore back this data to the previous earlier version before this T0 modified. Okay, this one is this technique is used especially in database. The database has this process called rollback. I think you have learned this before that. Everybody here learn database? Learn database? Some. Only one person. How about the rest? Have you learned database before? Yes. Have you method of this rollback. Okay, if the database has this feature, so if you are able to roll back, then the operating system you kill them, and therefore restore this, and T1 right now can successfully acquire this. Okay, this requires operating system intervention, and also requires the system to have this feature. Okay, we know database has this, no problem, but not all process has this rollback feature. If it doesn't have rollback feature, then it cannot allow the operating system to kill, because if kill, this will be lost. Okay, so only specific process which can roll back, you can overcome this thing. Okay, but still you have problem identifying deadlock, because when deadlock happens, you do not know. What you see is, or maybe humans see is, there is no progress. The program hacked. Okay, so there is deadlock. But the operating system will not be able to be aware of that. With later chapter, we will find how operating system detect deadlock. Okay, so deadlock is a serious case because once you get into this situation, you are not able to progress. Okay, so that's why each thread blocks one another, resulting in collective non-progress execution. That means this cannot progress, this also cannot progress. I showed to you is only two, but it can be multiple threads. It can be something like a circular way. This guy wait for this guy, 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 this guy wait for this guy. All of them are being okay, here is also circular way as well. Okay, this guy is waiting for this guy, this guy is waiting for this guy. Nobody is going to release unless they get hold of the resources. Same thing here. This one is not direct. It is indirect because it depends on the resources held by this guy. This guy also held some resources needed by other thread. It is one thing, another resource. So it's waiting for this guy. This guy is also waiting over there. This guy is waiting over there. That's why you get it. Okay? Okay, so that is deadlock. We will talk more about it in later chapter. But now I want to show you how you get into this kind of situation. Especially when you have multiple resources that you want to share. Okay, if you have only one mutex to use, or you only have one resources that protected by one mutex only, you will never have deadlock. Okay, so it's very easy. One mutex alone, shared by multiple threads, you will never have an deadlock. Deadlock only happens when you have multiple threads. Actually, we can see more conditions. I'll show you two conditions first. Two conditions to come to deadlock. The first one, you must have multiple threads that is sharing the data. Yeah? And then you have mutex that's protecting them. And you are acquiring more than one mutex. If you acquire only one mutex, no problem. But you start to acquire more than one, for example, in this case here, then potentially you can get into deadlock. And this is one example of how you get into deadlock. Unfortunately, it shows to you using producer-consumer process, but it doesn't need to be producer-consumer to get into deadlock. Any kind of process can get into deadlock, but the condition is like what is shown here. Here you have more than one mutex, and you acquire the mutex this way. Let's say, for example, I want to use resource 1 and resource 0 inside this critical region. Okay? So because this R0 is protected by mutex 0, R1 is protected by mutex 1, so naturally I will acquire, let's say, mutex 0, acquire. I don't write similar like that, but you know, acquire means wait. Okay? Okay, and then I mutex 1, acquire. Alright? And then after, because I acquired, if let's say successfully acquire mutex 0 and mutex 1, then in here I know that I can use these two freely because I'm the only person that is entering into this critical region, right? Okay, if I successfully acquire both of them. Okay, and now I want to free it. Mutex 1. and then mutex 0 release. Okay, you have to release over. That means after you acquire, you have to release. Okay, inside here, this is the critical region. Yeah, I can safely use these two together at the same time. Now, let's say this is the code for track 0. And my track 1, I also want to use these resources. Okay? But I write the code this way. I'm going to enter into my critical region. Okay, the critical region does not need to be the same region. Okay, this code maybe is a different code, but I'm using this same resources. Okay, it's different code. They are separate critical region. Okay, it does not need to be the same critical region. As long as you're trying to use these resources, you want to use it safely, you must make sure that this part is critical region. That's all. So mutex, let's say I do it this way. And then I do it this way. Okay, and then I free. Okay, sorry. And then mutex 1. Okay, if I do this, potentially I will get into this problem. How do I know? Okay, let's try it. First, thread 0, they all run at the same time, right? Let's say thread 0 managed to acquire mutex 0. Successfully acquired. Okay? We got it right now. We enter. But before we execute this thread comes in and then acquire mutex 1. And it also succeeds. This guy is slow. This one guy is fast. So both of them acquire mutex 0 and 1. And now they're here. And this thread will block because mutex 0 has already been acquired. So it's blocked here. This thread is blocked. Now this guy will try to acquire, but he's already acquired successfully by thread 1. Also blocked, so deadlock. You see the deadlock? Okay? So deadlock happened in this kind of situation. It looks like it's going to succeed, but then it failed here. Potentially it failed here, but not always the case like that. If you happen to be like that, then you get deadlock. Let's see another scenario which will not have deadlock. Acquire successfully, and then when this guy come in, he's slower. This already acquired, so he get blocked there. So this guy succeeded to enter, and then when he release, he will acquire, but block here. But when he release, he will unblock, and then access. The release. So no problem. Okay? So some scenario, no problem. But the scenario that I showed you just now will cause deadlock. But we don't want it, because if it can happen, it means that it will happen. Okay, we cannot say that, okay, some scenario can happen, some scenario will happen. So we say, just close one eye and pray that it doesn't happen. You cannot do that, because if you put your code in aviation, that means your plane, you have to pray, 50% you will crash, and then the plane will crash. So you cannot have this kind of situation. That means you must ensure that deadlock can never happen. So how do you overcome this? How do you overcome? Let's say you got two resources protected by two different resources, and you want to acquire them safely without deadlock. You can. What you need to do is you have to follow rules. Just follow simple rules. Thread 0, you acquire mutex 0 first, then thread 1 must follow the order. You must acquire mutex 0 first. Okay, if you follow this simple rule, then no problem. Let's change it and see this time if it change the situation. Let's change it to 0 and 1, so that is in order. But it does not need to be 0 and 1. If this guy is 1 and 0, you can change here. That means you swap it. So here mutex 1 first, then mutex 0. Also can. Okay, but make sure that this is 1 and 0. So here 1, 0, here 1, 0. If here 0, 1, here must be 0, 1. When you do that, follow this single rule, you will never encounter deadlock. Okay, let's see the situation. So the thread comes in, see who is faster. If this guy is faster, you acquire successfully, okay, and enter. But before you acquire this guy enter, right? And execute, and then try to acquire, because this guy already acquired min-tax 0, so you block. You block beforehand. Okay, you will now be able to acquire the next min-tax one. Both of them are fighting for the same min-tax first. Okay? The problem happen is one is acquiring the other successfully, and that happens only when you interchange them. But if you make them 0, 0, they fight for the same one, and who wins will enter. The one that loses will block here. He will not be able to acquire the next one. And cost it. You see that? Okay, you just follow this simple rule, you are fine. Okay? Just remember that, okay, when you acquire the min-tax, you have multiple min-taxes because you got each min-tax protects each resources. You must acquire them in order. Okay, one question here, I was talking only about the acquisition. How about the release here? You see, I also make this one 0, this 0, this one. Is there a problem there? Is there any problem there? Is it okay to release them in different order? Will that cause race condition if I release in different order? Huh? You said you don't think so. How about the rest? Do you think it will cause a deadlock? Some say yes. Actually, no. It's right. You will never have any deadlock when you release. Because when you release, that's how you remove deadlock, right? But you release in any order is fine. The only problem is when you acquire. When you acquire, you will potentially block others. That is the cause of the deadlock. When you release, you're actually making the other track to move. Okay, so when you release, in any order is fine. This way also fine. If you don't like it, you can switch it, also fine. Only when you acquire, you have to follow the rule. Okay? Now, you can, let's say your program is very complex, right? Very complex program. How do I know which one to apply? For example, I don't name it this way. I don't name it 0, 1. I might name it like this. That's not this. Okay? That's file. Then mutex memory. Then mutex printer, for example. Okay? So each of these mutexes will protect their own resources. Okay? So if you have the name, you name it like this, then I suggest that you name it with numbers at the back here. Okay? 0, 1, 2, 3. Okay? You give a name there. So if I want to acquire, I acquire in the ascending order or descending order. Ascending order means I start from 0 and then go on to a bigger number. Descending order means from a larger number to a smaller number. Okay, let's follow ascending order. That means 0, 1, 2. Okay, so when I acquire, I make sure that I want to acquire the 0 first. Then 1, then 2, then 3. Okay, in that order. Okay, the same thing here. I also will acquire in that order as well. Of course, you say it's kind of silly, alright. The problem is most of the time you're not acquiring the same kind of resources. Let's say, for example, thread 0. Okay, thread 0 only acquired these 2. It doesn't acquire this, it only needs this 2 at the same time. Okay? And then I have another thread. Thread number 1 is going to use only this 2. Okay? So this one is the one that is shared. This one maybe I have the more one. This 3 is it. Okay? 1, 2, 3. Okay? So you can see that this one 2, this one 3. So it doesn't need to, all of them need to acquire all the min-taxes because it depends on what you want to do, right? So let's say the black one represents thread 0, the red one represents thread 1. So thread 1 want to use this 3 at the same time, this guy wants to use these two at the same time. So how do you acquire the mutex? Same thing, follow the rule. So for thread 0, because it's a black one, so it's going to acquire like this. It's going to acquire this way. Mutex, hard disk, 0. Okay? And next is mutex memory. Okay? Because it's in ascending order, so I know that it's going to be same, 0 and 2. Okay? And this guy here is going to be this tree, and it must be in this order. Okay? So it must be mutex, hard disk, 0, okay, and then mutex, M, 2, and the next one is mutex, printer, 3. Acquire. Okay, so it acquired 3 resources, but then 0 to 3. Okay, I know that is in ascending order. In this case here, I'm very sure that you will not have any resources. Okay? Is that clear? Yeah, the thread do not need to acquire all of them, right? You can selectively select anyone that you need only, but when you acquire, make sure that the number is ascending order. Don't switch them. If you switch them, you actually have to replace them. If you want to put this tree at the top here, in this case here, there's no problem. Okay? But if let's say you have another thread that's coming in, 0 and 3, then no problem. Be safe, always do this. Okay? I know that he is thinking, oh, for this example, I think this printer can be put on top here. Yeah, put it. Okay, it will work. But then if your program change, let's say you got thread number 2 come in, thread 2 is using 0 and 3, now you got problem. Because this guy is following the rule, 0 and 3, and yours is 3, 0. So this guy will have the other guy. Okay? So you will have, you follow this rule and you will never get into data. Okay? If you have mutex that is protecting multiple resources, then you have to use that resources at the same time, like this. In this case, let's say R0, R1, R2. Then you can acquire the mutex in order to make sure that there's no misconnection. Okay? You can put ABC there, but I think using numerals because you can have as many as one. Okay? Alright. Another way to solve this problem is this, which is not so good. Let's say, for example, you know that, for example, these two is always used together. Then you use one mutex to protect these two. Only one mutex. Should say this. Let's say you got a printer, hard disk, and file, okay, and memory, let's say. Okay, you know that these two will always be used together, right? Then you protect using one mutex. Let's say call it mutex 0. But these two is protected by a separate mutex. Okay? So, if let's say most of the program or most of the thread is only using hard disk and file, they're sharing this. But because it's protected using only one mutex, so in this case, you don't have to worry about any further acquisition. You only acquire one mutex because this mutex actually protects both. Okay, but of course, this is not flexible. Okay, it's only good if let's say you know that they always use together. They are never used separately, so you can use one mutex to protect both. Okay, but most of the time, might not be in this case. Okay, sometimes you want to separate them to make sure that you can share the resources more effectively. Okay, so this is deadlock, and I showed you how it happens and how you solve it. This one is quite confusing because if you use user consider things, like actually it has nothing to do with user in any situation. Okay, and then it shows to you fix this. This is the problem. It doesn't show you how to fix it. Never mind. So I already finished that. Now we move on to the next chapter. Okay. Oh yeah, before that. Here's the place where they actually discuss about the fixing. So this is a problem they log, and then you fix it by interchanging. Okay. Now you see there are two names there. One is deadlock. Deadlock is the one that I mentioned here. This deadlock. The other one is starvation. Actually, here there is no starvation. I don't know why. Maybe it copy and paste from some lecture. These two are two different things. Starvation. They look alike, but they are different. Deadlock is very serious. Starvation is not serious. Deadlock, once you encounter any threat that involved in deadlock, they cannot progress, and that's it. They are gone already. Consider gone already. Right? And it's serious because your program cannot continue. What you do, of course, your data is corrupted. Okay? Now, how about starvation? Starvation is almost like deadlock, but it is not deadlock. Okay? Starvation means the thread is deprived from using the CPU. Okay? And how it happens? Let's say you got this thread. It is trying to access into these resources, but you got multiple threads here. Okay, let's say thread 0, and thread 1, 2, 3, 4. So whoever acquired these resources is able to use it. Let's say this guy, this four thread is very, very fast. Keep on acquiring and they succeed always. But this guy is slow. Okay, you try, you get blocked. Try, you get blocked. Try, you get blocked. Starvation. Okay, that means it's not deadlock, but it's deprived because it's slow or somehow your code is not, I'm not sure, something happened, and this thread always lose to all the threads, and he is the one starving. Okay, you have the resources, you are not encountering, nobody is encountering any deadlock, just that you are deprived from using and you cannot progress. It's almost the same like deadlock, but it is not deadlock. Deadlock means once you encounter that, they are gone already. This one no. If let's say some of them slow down, then thread 0 is able to use it. Okay? If they are fast, very fast, then this guy is deprived from using this and he is starving. Okay? So that is starvation. And here, it's not talking about starvation, it's talking about deadlock. Because starvation is something that I mentioned before. Okay, I move on to other topics. Now, next chapter. Okay, here is still L4, actually it's right as well. Okay, I think I mentioned last week about monitor, right? So Matrix has a problem because you have to acquire and release. Okay? Why you can have problem? Let's say your code is like this. Let's look at one simple example. Why it can be problematic? Let's say you have something like this. Matrix wire. Okay? And then you do some job here, and then here maybe there's a condition. Okay, and then you let's release. Okay, if condition 2, you don't release, else maybe you release. So when you run the code, of course, this one is very easy, right? Because the program is quite simple. You acquire and you release. There's no if-else statement. In this case here, there's so many if-else statements, and some will release, some does not. And if your code have multiple if-else statements, it's very hard to see, isn't it? Whether you release or you don't release. Right now. So this is a problem. Okay? And your program is not always like this. Your program is more to this, right? You will have a lot of condition here. That's why you have program. Now, if certain condition happens, then you do external action. And sometimes you want to release. Sometimes you don't want to release. You want to release elsewhere. Okay? So you cannot be sure whether you release or not. Okay? And that's the reason why we have monitor. Okay, let's look at monitor. So monitor is actually, especially Java, actually how to write. So you got function as a void, and then you synchronize. Maybe you never use this word. This word, that's fine. I now tell you that this actually is the monitor. You can synchronize. Put your code inside there. You can have all if-else statement. Nested if-else statement is fine. Once you enter, one. Okay, if you forget to release anyone here, when you get up, you will automatically release it. Okay, so you don't have to worry. Because the code block is going to release for you. If you forget somewhere, you will ensure that when you get up, you will automatically release it. Okay? Now, of course, you say, okay, I can do the same in a fast. Where I enter, where I release. But sometimes it's not so easy. Because in Java, you can call a function, and that function can throw. So when it throws, okay, if it throws, it will get up from this function, and then it will not execute your mutex release here. Because when it throws, here it will catch, it will throw. It will throw out without executing your mutex release. Okay? But then if you put in the code block of this, Java will ensure that it will release. So when you throw, if you don't catch it, you will throw again. But when you throw, because it get up from this code block, right? And you automatically release. Okay, if you write the code here to release, you will not release because you will not execute this code. Okay? But Java will ensure when you get up from this code block, you will release. Okay. C++ does not have this keyword. It does not have this keyword synchronize. Actually, it's synchronized. You don't have to use with the function. You can actually create a block itself. It's synchronized. It's synchronized like this inside function. Okay? Here I use the function body as synchronized, or you can use it independently like this. Okay, in C++, we don't have this keyword. How do we implement? We can implement it. We use I can't remember what it was. It's inside one in the practical. There's a name for it. I think it's called mutex. Mutex something. But it's not a normal mutex. This mutex is I'll tell you later what is the name for it. It's called mutex unfortunately, but actually it should be called monitor because this is monitor. Okay? But the name used in C++ is mutex. I can't remember what it was. Okay. Now when you create it, okay, and it will be created. This is the object. Okay, it's created inside this code block. When you get out from this code block, what happens to the object? C++ will automatically destroy it. Okay? So when it destroys, it will call the destructor of this object. And the destructor will release the mutex. So effectively, using this object in C++ will give you the same functionality as synchronize. Okay? Except that on entering, you have to create this object. If you don't create this object, then you will not have this this kind of protection. So whatever that is inside here after this mutex is critical region. Okay, up to the point where you close the square. So you just create the object only. You don't even have to apply. Because when you create, you apply automatically. When you get up from this block, this object is deleted. When you delete, the destructor of this object will release the mutex. Okay? Whereas here, you don't have to create the object. This synchronizes itself will do it. Okay, so this is monitor. Okay, there's another one that is missing here. This. You just create this object. I can't remember what the name is. I think is in practical 5 or 6 years. If we will come to this. No, you don't have to do anything. You just create the object. Because when you create the object, you will run is the constructor. In C++, you got a class, and your class has constructor and destructor. Do you know that? Okay, whenever you create the object, you run the constructor. Whenever the object is deleted or removed, you run the destructor. Do you know that? Okay, if you don't know, you can try and look up on constructor and destructor. So what you create is, you call the constructor of this matrix, and the matrix will automatically acquire itself. Right? And then when it deletes this matrix, you will call the destructor. The destructor will release the matrix. So, and if you create an object inside a code block like this, okay, it will live within this code block. When you get out from this code block, whatever that you created will be deleted, right? C also the same thing, right? Any variable that you create in the code block, when you get out from the code block, is all deleted, right? So it's the same thing. The object is deleted. So when you delete, you call the destructor of the object matrix, and then you will automatically release it. Okay? So that's how you implement the monitor. Now, so the monitor actually help improve programming experience, especially if you have this kind of problem. Okay? You have if statement, throw, try catch, throw, and all that. Now, and there is another which is not written here. Discuss with you. That because it's quite useful. It's called conditional variable. Okay, so we have semaphore, complete semaphore. We got mutex, we got monitor, and then we have another one, conditional variable. This conditional variable, to me, I like this the most. Okay, the name is kind of funny, but then it's very useful. One thing is, it is just, I can say it is the most generic. Yeah, you can use conditional variable to implement semaphore. You can implement mutex. You can implement monitor. Okay, it's the most generic of all. Okay, so how does it work? Now, in order for the semaphore to block, you have a counter, and that counter needs to decrement until it becomes 0. When it becomes 0, you block. Okay, that's why producer consumer, when we implement it, for the consumer is fine because consumer, whenever you consume, the item reduce, right? Reduce to 0. Okay, but for producer is difficult because the item increasing, not reducing. So we have to change the formula slightly to make it decrease. Instead of looking at an item, we look at this one. Because the this one becomes reduced as you increase the amount. So you have to think that way. When you use conditional variable, you don't have this problem. Because you can have the condition, that's why it's conditional variable. You can have any condition, you can create any condition to block it. You say, let's say the count is 10, wrong. Then you specify the condition. The condition is, the item is 10, then you block. So it's more flexible than counting semaphore. Okay, so you can, it's generic, that means you can implement counting semaphore using the conditional variable. Okay? And how it is used, I'm not going to discuss, you can actually look it up yourself for conditional variable. Actually, it's very, very useful. Especially if you encounter a problem where, like for example, producer, consumer, for the consumer, it's easy to use counting semaphore, but for the producer, it's very hard. Think how to actually create a formula to counter it, right? So you use conditional variable. In fact, you can use conditional variable to solve producer concept. And it's much easier. Because you don't have to think about reducing the 0, okay? Or how to make your problem to become, to work in that way. Because you have conditional variable, you can work in that, whatever condition that is specified. Look it up if you're interested, because we are not going to study here, so I won't discuss it. Okay, so I already discussed monitor. Next thing is this. Whatever we discuss here is important, and it's only for one system, one computer system. That means your processor is in one system, and they can communicate with one another, right? So they synchronize using this, we call it inter-process communication. Inter-process communication. Okay? And what are those inter-process communication? Counting semaphore. Okay, and then the text, monitor, conditional variable. Okay, many more. So all this we call it inter-process communication or IPC. Okay, so this IPC is only for single system. It's easy. Okay, we implemented that. We have libraries for that. But how about if we want to share resources across distributed system, not in one system? Okay? Now we have a problem because we cannot use counting semaphore. Because counting semaphore and all this is only working on a single system. Okay? That means the processor needs to be nearby. Okay? And operating system needs to be aware of this. Now, if a distributed system, we cannot use this, how do we solve it? We still have the same problem. We have to acquire the resources because there are multiple distributed systems trying to access into the same data, and they are going to race with one another. So race function is still there. How do we overcome it? We use token passing, one of the easiest ways. There are many ways. We're going to discuss token passing. And there are two algorithms that we're going to discuss. Actually, there are many more. There are a lot more. We're going to look at two. Okay? So the token passing is like what we suggest. Pass along this token. Whoever got token is the one that you're going to enter into the region. How many tokens you have? Only one. Okay? You have only one, you pass along. So whoever has the token can enter the particular region. So let's say, for example, you have the token. I'm another system. Okay? So I have a request from you, and then you have to pass it. If you're already finished using the particular region, then you pass it. So if you ask me, I have the token, then I can enter into the region. So by having this kind of understanding of how we use the token and how we pass the token, then we can ensure mutual exclusion in distributed manner. Okay? So how do we implement it? Let's have a look. There are many ways to do it. One of the ways is Suzuki-Kasami algorithm. Okay, I'm not going to use this slide here because this slide is very hard to explain. I think there's a formula there. Somewhere it has this formula. I don't need to understand this. Okay, I'll use YouTube to explain. Okay, I actually managed to extract the information for one. I should not be clear as well. I managed to only extract one. So I'm going to explain using slide for the first one, and the second one will be watching. I'll give you the link as well where to find the actual source. Okay, I put in the slide so that I don't have to play. So I already extract the image from here. Click on this. This is the explain how it works. Okay. It has no voice there. It is just showing pictures. Moving pictures. Yeah? So I don't think that okay, so in distributed manners, we have multiple sites. Okay, they call sites there. So there are 5 sites. And each one of them wants to access into the critical region. Okay, use shared resources, and they have to ensure that there's no risk condition. They have to acquire the components. Okay, so let's see Suzuki Kasami. Suzuki Kasami algorithm is an algorithm first published by the author Suzuki and Kasami. Okay, what do you need in order to do this token passing for Suzuki Kasami? First thing is you need to have queue. I shouldn't say queue, I should say the argument. It's request. Okay, request. Okay, and then what else do I need? I need to have token. Okay, I'll tell you why we need this. What is the goal of this? So in this token, I have 2 things. First, I have token key. Okay, and then I also have another information, which is class. Okay. So there are how many variables that I have? I have an array of request number. Okay, queue. The queue is to queue up whatever one request for the token. Class number is something similar like this. Request number, it has number inside. Okay. Okay, so this is inside one token. Okay? This is the token that we pass it on. Whoever has get hold of this token is eligible to enter into the critical region. Okay, the rest, once the access to the critical region, he has to request from whoever will have the token. Okay, and then this token eventually will be passed to the requester. When the requester receives it, he itself can enter into it. But token passing and also acquisition of the token is only one step. The thing is, you have to keep track of all this to make sure that the operation is successful for all. Yes, so that's why we have queue and class number. Okay. First, I'll explain the step first, and then I'll explain the reason why we have this. Okay, first thing is the site has this RM, request number, and this request number has the number of elements inside it, and the size here depends on the size of which should be the same as the size of the site. So I have 5 sites there, so I should have 5. Each one of them is for each one of the sites. Okay, so let's say okay, so this is for site 0, site 1, site 2, site 3, site 4. Okay, so each one of the sites will have this. Okay, that means you have to know the rest of the site who is participating in this automatically. Okay, by site, every site will keep track of one another's request number. Okay, what is this request number? It's ready to show up. First, we have this request number. Now let's see what we mean with this request number. First, we start with 0. All of them are 0. Okay, all of them is set to 0. Okay. Now, if let's say one of them has the token, let's choose one. Let's choose. Okay, I'll cover this in a while. Let's choose one of them to have the token. This one's selection. one side will be the open holder. Okay, this one. It's the same. Again, because he's not discussing about that. They are follow what he explained. Okay, I don't now I don't assign the token to anyone. Okay, I just want to show to you how do we request for the token. Okay, here I do not show who has the token, but let's study how we request for the token. First thing is one of them needs to, whoever wants to request for the token, he has to send a message. Okay? So that is called request message. Request message. Okay, you send the request message, and this request message has two information. The first information is the requester ID or requester number. Okay. And the second one is the request number. Sequence number. Sequence number is okay. So let's look at the site one. Site one like to ask for the token. Okay. So what it does, it asks. One thing here is it doesn't know X the token, so it just asks all. Okay, how does it know all? Because in this database, you know all the site, right? All the site. So it knows who is participating. It's going to request for all of them, and it's going to send the same message. The requester number, that means its phone number. And then the sequence number, you look at this number. At the moment, before it's sent, you look at when it's on the line, isn't it all zero? Zero here, right? Okay. Its phone number. Okay, this element is for site number 0, site number 1, site number 2, site number 3, site number 4. So its own site is 1. So we look at site number 1. That request number is 0. So when it sends the first message, it will be sequence 1. Okay, sequence 1. So when it sends this number is 1 and itself is 1. So that's all count 1. Okay? And it sends all. It doesn't know who is the token holder, it just simply sends all. Okay, at the same time, it also update its own request number to 1. Okay, it set its own one to 1 because now it has to make sure that this number, request number, on its side will not set. Okay? Now, on the rest of the site, when you receive this, whether it's open holder or it's not open holder, when you receive a message, there are two things that you have to do. First, you have to check. The request needs to be greater. The sequence number here needs to be less or equals to the request number of that site. This I. Okay. So what does it mean? So let's say I am site number. Yes, okay. So I check my phone one, so this is RN2. And the message comes from the requester is 1, so 1 here. So assume that this is 1. That's not 1. This is this 1, 2, 3, 4, 5. Okay? So index number 1 is 0. Okay, so 0. Okay, and then this is 1. So we check. If this number bigger than the sequence number, if it is bigger, okay, if it is bigger, then that means this is okay. Okay. If this sequence number is bigger than this request number that you hold, then that is the latest one. Okay. So you have to check whether the information that you receive is outdated. Okay, so this step is actually to check whether the message is outdated. Okay, so let's talk about our latest message. Whenever I send, right, sometimes I receive, I update it. Some of my messages actually go elsewhere. Take a very long path. Eventually it arrives, but it arrives after some time. Okay? And that message is the old message. So how do you distinguish between the latest one and the one that is old? Easy. Put a number. That's what you got. Request number. Alright? So that request number is going to tell you whether which message that is sent is old, which message that is sent is new. Because as you send a message, even though you send early on, you expect the early on to arrive, right? Sometimes it goes elsewhere. The second message that you send arrives first. So the first message that goes elsewhere will come after you get to the destination. When you get to the destination, it comes after the second message. That means the first message is outdated. Right? So how do I check whether it's outdated? I use this number, this request number. Okay? So this request number will be updated whenever I receive the message. So initially, if let's say my number, my requirement is 0, but the message that I receive, sequence is 1 from this requester. Then I know that this message is the latest one. The one that I have before was the old one, right? So this is not outdated. Not outdated. Okay? Now, if it is not outdated, then I can update it. Update it to. Okay, that's why here when you receive, you check. Let's say check. Okay, see here 2. 1 is inside here 1 is because it comes from requested number. Okay, or F2 is this one. 1 is this one. Currently is 0. But when you receive it is 1. The sequence number is 1 from the message. So it's bigger than the 0. That means you know that is not outdated. It's the latest one. Okay? So you accept it. All of them will accept it because all of them you can see that 0, 0, 0. Okay? So it knows that the message coming from this requester is the latest one. Okay? For all of them. So they're going to update it. So they accept it and they're going to update it. So all of them. Okay? Alright? Okay, let's say for example, I send one first, send this one first, and then I send this one second. So I'm using my scenario just now. Okay? Let's say this one goes, don't know how to, right? But this will arrive first. So initially you see your code RN, okay, is 0, let's say. But the sequence number that you receive is 2. Is it 2 is bigger than 0? It's bigger, right? Then you know that this is not outdated. It's new. It's not outdated. Okay? So you're going to update your R and I, J, as T. You're going to delete this and then you update it. Now somehow this message it goes elsewhere, eventually arrive. Okay, when it arrives, your SN now is 1, but currently you have 2. Then you compare. Is it smaller? It's bigger. It means you know that this one is outdated. Understand? So you use this number to find out whether the message that arrived outdated or not. Okay? You will use the latest one. Okay? You will not use the old one. The old one that comes, you will just ignore it. Okay, so that is the reason the request number is there. Okay, I use the request number to check if the message that coming in is the latest or not latest. And this happens in distributed manner. We can distributed system, we cannot avoid it. Okay, because when we send a message, we don't know where the message will go, how it arrives. Okay, so you want to check whether the message is outdated. If outdated, you just throw away. If it is not outdated, then you update yourself. So when you update, all of them will update it to this number. Okay, so all of them will know that this R1 wants to have open. Okay, so let's say right now, suppose site 5 has the open. Okay, so site open is open now. It can, let's say you already use it. It's already over the legitimacy. Now you can pass this open to the requester. Okay, so how does it do? You check this number here, and it will check with this last number. I'll explain to you later. And that's how it knows whether who wants the offer, because it will check the last number. I'll explain to you later. Okay, so at the moment, just know that this site number 5 realize that site number 1 is it, and you can send this site. Sorry, you can send the token to the site. Okay, now, so what does it do? It does this. First thing, it looks at the last number. Now this last number is something similar to the request number. You keep it separately, and this last number is together with this object. This key is also object. Just assume that this is one object. Okay, one of that, it contains 2 variables inside it. Okay, initially it will be 0. Okay, and then this will be empty. And if I receive the sequence number, that means the request with the sequence number 1, eventually I'll update my request to 1, right? Okay, let's see this is site number 5. Okay, site number 5, you receive the request number, the request number is 1, it's bigger than 0, so you update it. Okay, now, before it passes the token, it needs to know who actually wants the token. Okay, it will not know from which request number. It will only know by comparing this request number to this last number. Okay, so this last number indicates who has already been serviced. Okay, so you look at this. Request number is 1. This is 0, meaning that this guy has not been serviced yet, because this number is bigger than this. Okay? If it is the same, that means it has been serviced. Okay? And how come it gets to this number instantly? Because everybody, when it finishes doing it, using the open already, come up with a critical region, he has to update this. Okay? So whoever finish using the open, update. Okay? So when you update, it will be the same one. Right? But at the moment, site number 5, see this request number is 1, and it's bigger than this last number. So it knows that this is outstanding. Okay? Outstanding request. How does it know? We have the formula somewhere. It compares this number, request number, for site number 5. Okay, the requester is 1, so you check requester number 1, and you check with the last number. Last number is LN. Okay, LN 1. Okay, so LN 1 is 0. RN 5 1 is 1. Okay, since this is bigger than that, then we know that this is outstanding request. Okay, so I know the outstanding request if my request number is bigger than the last number of this token. Yes, so that means this token keep track who actually use already the token. Yes, so it will keep the last number of the request sequence number that has been serviced. Yeah? If the request number that is coming in bigger than the last one, this one has not been serviced. Okay? That's why you call it obsolete.
我用 iPad 是哦，知道。
Request means I want to use the
在这里啊，
referring
今
to
天我
actually
就
that message is just tell the site that we want to use the number. Okay? The number that you want to order is the request number. Okay? Well, you have to understand that the request number is the request for one to use the number. It's not the request. The request message is just carry the information. Correct? Yeah? Right. So now it knows that is requesting, so it's going to put this into the queue. Okay? Okay, it knows that it's going to use, so it's going to queue. But it hasn't serviced yet. You don't change it, right? It's still 0. Yeah? And then it will pass this whole token to site number 1. Okay, site number 1 will receive this whole token. This token will have the queue information, will have the last number information. Okay, this token is an object, it contains this information. So site number 5 updated, and then pass this whole token to site number 1. Okay? So site number 1 when you receive it, receive that, receive this token, okay, and then it will use that token because it wants to use, right? So you use that token, you enter the critical region, and once it finishes using the critical region, come out from the critical region again, you do this. Because it's already service, right? This is his request. This was the last number. Now it has been serviced, so it's going to update this. It's going to update this. To indicate that he already used the token or that sequence number that he requested. Okay, so this update is done by site number 1, not site number 5, that's site number 1. Understand? Right. Yeah, that is done by site number 5. Site number 5 queue site number 1. And then it passes the whole token to site number 1. Site number 1 receives the token because it has the token, you enter it with the region. Alright, after you get it from the critical region, he has to update this token. He has to update the token to indicate that I have been serviced. Okay, and then you remove itself. Okay? You remove itself and then I have been serviced. So we put 1 here. So right now, the request number for all the sites, including site number 1, and the last number inside this token is the same. It means that this sequence number of the request from site number 1 has been serviced. Okay? So it will not be serviced again next time when you pass to another site. Okay? So why this is important? Because this token will pass along, right? And the queue will tell who is waiting. And the last number and the request number is going to check who is outstanding so that it can put the site into this queue. Understand? So you use the queue to find out who is the last number. Okay? And you use the request number and the last number to check which request is outstanding. If the number is the same, it means it has been serviced or outstanding. If this request number is bigger than the last number, you know that it's outstanding. You have to service it. And because of that, you know that this belongs to site number 1. And we will queue that site into this queue. Is that clear? Understand? So that's how Suzuki Kazami works. Yeah, let's look at some example. Okay, this one I just explained why I explained this one. When you get up from CSPC region, you update this to here. Okay, you put this into this. Right? Actually, I should know this. So because this is true number, I should actually use this. suppose things has been exchanging, the message has been exchanging, and object has been used. And right now what you see is here, this kind of situation. And after multiple exchanges, and this is the situation that we have. Okay? So the token holder is 2. And everybody is synchronized, everybody knows that their most recent request number. Okay? At the moment, all of them are synchronized. Okay? Now suppose set number 5, one of the object. So it will broadcast 585 is followed by 8. 8 is because it looks like here 8. 5, right? 1, 2, 3, 4, 5. It's all 1, is 8. The sequence number is 8. So before that is 7. So increase by 1, 8, and then it's 7. Okay? So the rest, because it's 7, and they're receiving 8, then it knows that this is not obligated. It's new one. It's not obligated. It's new one. Right? So all of them is going to accept the request. And then you update this 7 to 8. Okay? Right. Let's say at the same time, site number 1 also wants the token. So it also will broadcast. Okay? It will broadcast as well. So its own site number is 1. So it's 1. And then before that it was 5, right? So it increased by 1. So it becomes 6 because you want to request. So it sent that message 6. Okay? And the rest will check. Site number 1 is 5. But the message that you received is sequence number 6. So you know that it's not obligated, it's new. So they're going to accept. Right? They accept, they're going to update it to 6. Okay? Now next. Let's say another site number 3, this one site number 5, then number 1, now number 3. So site number 3 also wants a request. So it put its own ID 3333. And then before that, number 3 is 4, right? So when you request, it will be 5. It will be a new one, you request, so it will be 5. Okay, and I send it out, everybody will see 4. And then the new one that's coming is 5. So like this is not obligated, it's new one. Okay, so you will accept it and you will update this one. Okay, so there are 3 requests there. Okay, and all of them receive the message, all of them update their request number. Okay, okay, so let's say for example, just now, why site number this does not take action. The reason is because it's in the critical region. Okay, all is in the critical region, the message now. Okay, when the message comes, it will update it, but it's still in critical region. So it's not free to give away the token yet. It's still using. But right now, suppose it's finished. It's already finished using the token. It's coming out from the critical region. So what does it do? First thing it does is it will check for outstanding requests. Okay, remember this formula? Okay, you check this formula. You check if here is +1 because you know that it's bigger, right? It's bigger by 1 over the request is always 1 bigger than the last number. So that's why it's +1. So if this is equal to this +1, that means it is outstanding. Understand? I use this formula, but you use that formula. Actually, it's the same. Okay, because we know that the request number is always 1 ahead. Alright. So if you +1, that means this one equals to LN plus 1. If they are equal, that means it's outstanding. So it knows that the site is outstanding if this equation is true or this equation is true. Okay, it check with the last number. Okay, and then it will check with the request number. Last number of that problem. The last number of that problem is 5427. Okay. Let's get this. At the moment, this last number was 5427. 5427. So that is the last number. Okay. Let's look at the current synchronized request number. The request number for all right now is 6. After the exchanges is 6 3. So this one is the last number. So when it comes out from the critical region, we will do that check. So let's see. So we can see from here. This is bigger than that, right? That means site number 1 requested. So it knows that site number 1 requested. So it's with the queue. With the queue. Okay, 2. 2 is also sorry, 2 because it's set, right? So it's going to update because it comes out from it comes out from the critical region. So it's going to update this queue. Yeah, I put red color. This is because itself come out from the critical region because it's serving its own request. So it's going to update itself. Okay. Now this 5 and 4. So it knows that this one is requesting. So we put 3. Okay. Okay, next. See 2 no change. 8 7. 8 is bigger, so you know that this is also requesting. Okay. Second. And who is not requesting? Number 4. Number 4 is not requesting because it's 2. So you know that 4 is not requesting. But if you look at the example just now, site number 5 request, site number 3 request, okay, and site number 1 request. Right? So all of them will be inside the queue. Okay? So it's inside the queue, and then this is not changing. It's not changing. The only one that changed is this 3. Okay, I write it 2 before. Change to 3. Why? Because this is itself. Okay, it was serving itself just now. When it got up from the critical region, it already serviced itself, so it has to increase itself. Okay? But this one is not changed. This one is not changed. Still difference there. 6 5 5 4 8 7. Okay? But what is placed inside the queue is the number. One who is outstanding. The request that is outstanding. So this is outstanding, so it's going to be there. This is outstanding. Okay, and this is also outstanding. So 1 3 1. Understand? And which is correct because just now it's only 1 3 5 the request. Okay, so that is how this site number 2 knows who actually is requesting. And then he will help put that site in the queue by looking at this number here, the site. Okay, so this whole token here is going to pass to the requester. So who is the one that is going to receive? Because it's the queue, it is going to take up one by one. Maybe from 1, so it's going to take up this. Okay, so it knows that 1 is requesting, so it's going to take up and pass this token to 1. Okay, site number 1. So site number 1 will receive it and then use the token by entering into the critical section. Okay? Okay, so it's going to now come up from the critical region. Okay, critical region, critical section, and you will do the same thing. You check. First, you do itself first, because it's site number 1. It is already serving itself. So 6 5 here, it served itself already. So it's update to 6. So when I update to 6, I should have round it off. Yeah. Update to 6. Because it already served itself. Alright? Now it will check the rest. 3 3, no outstanding. 5 4, there is outstanding. So first it's checked in the queue. Is it in there already? Find out, yeah, 3 is already there. So you look in no program because it's already in there. Okay? And then go 2 2, no outstanding. 8 7, outstanding. But it checked number 5. Number 5 is there, so you know. Because it's already inside the queue. This is the algorithm described the system as. Yeah, correct. Yeah, it's right. That is how it does it. So we don't follow the algorithm. Okay? Yeah, the algorithm is described in this way. So every time you come out, you will do check. Okay? Of course, it's kind of silly to do that, but that's how it does it. Okay, you check again, and if it is not in the queue, you pull it. If it is already in the queue, you will not do anything. Actually, there's a good question there. You ask why it has to check again. Okay, what happens if, let's say, when you receive the topic is critical region, somebody send a message, this will be updated. Okay, let's say, for example, 4 requests, now it becomes 3 again. So that means he has to check all over again. Because while it is in critical region, new message will come in. So every site have to check. Yeah? If it is already in the queue, don't do anything. If it's not in the queue, no. When it comes out from the critical region, now they check. Yeah? Critical region is, okay, token passing is actually attack risk condition, right? So if you want to use certain resources, you need to know that you're the only person that uses the resources. The only way to do that is to ensure feature execution. So in this alternative use token passing, you have the token, you have access. Right? So when I say critical region means you are entering into this environment where when you share, you safely share. Because it's the major execution function. That's very good. Or great intersection. Yeah, no, it's not used for use the token to collect the resources. Is that? Yeah, you see, can you inside the region? Okay? So you have the token, you can enter the region, and you know that you're safe to use the resources because you are the only person, right? The only person that is in the critical region. No one else can enter because they don't have the token. Okay? So you update it, you check to see whether it's outstanding. If it is bigger, you know that it's outstanding and you are not in the queue, you add it. Okay? And you will add it if you have to check again and again because all it is in the critical region, new messages will come in. Okay, so this number can change. Therefore, it might not be inside the queue. So let's say 4 requests, it become 3 here. Okay, so when they come out from the critical region, you see that 3 and 4. It knows that 4 is requested, but it's not in the queue. Okay, but in this example, of course, 4 is not requesting, so it will be 2. Okay. Now, once they already service, it sees that the queue is not empty, so it's going to move to the next one. And it knows that site number 3 is the one, the next person that will use it. So it sends this whole token to site number 3 by removing it from the queue. And site 3 will receive it and it will use it. Once you use it, you come up from the critical region, you do the checking again. Okay, and you find out that 8 and 7, and this is the standing one, but it's already inside there, so you do like that. Okay, next. Of course, you also have to update that because you already served itself, so it's going to update itself to 5. Okay. So this last number will be updated by the requested itself. That means after you use, you update this whole server means it has been serviced. Okay? Alright, so next, you send this token to site number 5. Site number 5 will receive it and enter the critical region. And when it come out, you do the checking, and of course, you update also. This 8. Okay? And then you see there's no more outstanding requests. Okay, no more outstanding requests, and therefore nobody else is sent, and you just stay there. Okay, you stay to site number 5 because nobody is requesting. That token is held by stuck in the front. It is not released to anyone, it's holding it. Okay? Because it's not using it, it's just holding. Whoever requests, you get into the queue, and then you start disseminating it. So that's how Suzuki Kasami is. Okay? Yeah, it's quite simple, right? Okay, so this is a step that is used by Suzuki Kasami to ensure that token is passed safely on another, and it knows who actually requested. And by using this token passing, only one token is passed, and this one token will ensure mutual solution in this token. Okay? So it's quite straightforward. Okay, next. I will go into this because I already explained before, right? It's whatever I explained to you just now. And actually, for this whole meeting, I'll share with you this. Okay, if you don't want to watch this, you can watch it. The video actually is just moving animation, just what I showed you. Now, the next thing that I want to talk about is another token passing. First, I want to discuss the limiting, the problem with this Suzuki Kasami and how can it be improved. The other algorithm is called Raymond's algorithm. I'm going to use the same guys. Okay, before I get into here, let's discuss the problem with this Suzuki Kasami test. Okay, if you look at Suzuki Kasami, several things that you can see. First thing is, all the side need to know everybody. Okay? He needs to know everybody. And he has to keep track of every of the request number of all the side. Okay? That means all the side needs to know everybody. He has to keep information about everybody else. Okay? You got 1 million people sharing token, then you will have 1 million entries. Okay? One thing. Second thing is the token, you have a queue which is going to be long, and this one, last number is going to be random. Right? Okay, so that is one disadvantage. The second disadvantage is all the site that you want to use the token have to broadcast to everybody. Okay, it does not know who actually has the token. It has to broadcast all. You have 1 million participants, you have to broadcast to 1 million all participants. It is 1 million participants. Okay, so you're going to use a lot of bandwidth in order to disseminate this information or request the token. Okay, so that's why Raymond is come into the picture. Raymond is his name. He's an Australian. He said, I want to cut this down. First thing is, I don't want all this. This is request number. Okay? And of course, if I don't want the request number, that means I can keep track of the latest on how do I grab. So that's the question. Second thing is, this token, we don't have token because I'm passing, but I don't want this key. I also don't want this last number. Yeah? So you cut down all this. If you cut down all this, then you need to make your operator aware who is requesting. And how does it make it aware? Actually, it does not cut down this. Move this away. Okay, move this into somewhere else. This queue is still there because you need to grab it to actually pass it. So you move it out. But you don't have this last number. This one, last number is gone. Or you have to replace it with something else. Okay, the next thing is, the biggest problem is you don't in Suzuki Kasami, you have to disseminate or you have to broadcast a message to all participants. In Raymond's algorithm, you only pass from your parent. You ask the parent, okay, there's a parent account, ask the parent, okay, I want token. And then you let the parent decide token. You only ask the parent to do it. Okay? And the parent, if let's say the parent has no token, you will ask his own parent. Okay? So basically, the the Raymond's algorithm form some kind of a network, tree network. Because I mentioned about parent and child, that means you know that it forms a tree, right? You will form a tree network, and therefore you have this parent and child relationship. Let's say I have several subsets. Okay? First thing, they will form a tree. And how do they form the tree? They will form a tree like this. If this guy is the bottom board side, that, so he's going to be the root of the tree. And everybody is going to point to it. Yeah, everybody can point to it by change of subdivision. You can be doing like this. Point to somebody else, the parent, who does not have the coordinates line. This guy maybe